Hi everyone, so in this video we're going to look at how complex numbers can be used to help solve problems involving periodic models. So on screen you can see two graphs, both of periodic functions. They're both sine functions. And you'll have seen already when looking at sinusoidal functions, those are functions involving sine or cos, that the general form that they take is we have some function and then a sine of bx plus c plus d. And you looked at what those various constants a, b, c and d can be used for when interpreting the graph. The thing that we're most interested in for these types of questions is we know that a is our amplitude, so that's our maximum displacement from the principal axis. If we're looking at this blue graph, there's my amplitude there, the principal axis is just the x-axis in this case. And we know that c is the horizontal shift. Now, that's what we've called it up until now. I'm actually going to call that the phase shift. It means exactly the same thing. And we also remember that d is corresponds to our principal axis and b is related to our period and frequency of our curve. Okay, so what is phase shift? Well, phase shift is just the horizontal shift. If we're looking at this first function, f of x is equal to sine x, we can see that that has a phase shift of 0. If we're looking at our red function, we can see that has a phase shift of pi over 2. It's just the number that's added or subtracted from the x within the brackets. And so we can also talk about the phase difference between these two sinusoidal functions. It is just the difference in their phase shifts. Pi over 2 minus 0 is just pi over 2. Easy. Okay, so how do complex numbers relate to sinusoidal functions? Well, we can consider the imaginary part of a complex number as a sinusoidal function. What do I mean by that? If we have some complex number z, and we can write that in Cartesian form, a plus bi, and we could also write that in Euler form, modulus argument form, r is our modulus, theta is our argument, and we can also write that in cis form. And if you've forgotten, remember that r cis theta means r times cos theta plus I sine theta. Okay, now in our Cartesian form, we know that a is the real part of z and b is the imaginary part of z. So looking back at this cis form, if I multiply out, if it helps you see it a little bit more clearly, we can see that the imaginary part, i.e. the bit that's multiplying the I, in fact, let's write that round the other way so it's really easy to see. We can see that r sine theta is the imaginary part of z. That's our b in Cartesian form. So I can write, in summary, the imaginary part of a complex number z is going to be, well, let's just write that in all the forms we can. R e to the I theta, so the imaginary part of the complex number. Again, I'm just rewriting what a z is over and over again. Okay, you might want to remember that that's also r cis theta. So the imaginary part of this complex number z is just r sine theta. That's going to be incredibly useful. Why? Well, if you look at that, r sine theta, that is a sinusoidal function. If you imagine a graph of theta on the x-axis and some function, this function of theta, f of theta, is equal to r sine theta. So our imaginary part of our complex number is a sinusoidal function. And we can also see straight away, well, the amplitude of this function is r. So this is my amplitude. And in this particular example, theta is just the angle theta. It doesn't have a phase shift at the moment, okay? So being able to write the imaginary part of a complex number as a sinusoidal function is incredibly useful. Why? We're going to see in a moment. So, if we have two sinusoidal functions, same ones that we saw before, the blue function on this graph and the red function on this graph, we often are interested in adding these two sinusoidal functions together to give us a third sinusoidal function, which is that green graph you can see. So f3, which is f1 plus f2. So for example, in real life, if you have two alternating current electrical sources, and they're combined. So each of those functions, the first function, the second function, might represent the voltage output of an electrical source, and it's alternating. That's why we get a sine wave. And often if we combine those two sources, we want to know the amplitude and the phase shift of that resulting third function. Okay, great. So we can just add the functions together. So if here where I've got the third function is equal to the first function plus the second function, let's write out what that actually is. So that's sine of x plus sine of x plus pi over 2. Okay, now that's a function, and I can type it into my calculator and plot it. And you can get things you need from your calculator, but what if you didn't have the exact values? You need to know how to manipulate it. Now, the problem we have looking at this function, if I want to know the amplitude and phase shift of this function, I can't just see it. So remember, when I have the general form of a sinusoidal function, let's write that up here, f of x is equal to a sine x, bx plus c plus d. If we have it in this form, we can immediately see the amplitude and the phase shift. But looking at this green function, f3, down here, I can't see that. It's not helpful. I've got two sine functions added together, so I can't immediately see the amplitude and the phase shift. Okay, so what can we do? We can use the fact that we learned, or the little manipulation that we did with our complex numbers. So remember, the imaginary part of a complex number, so that's the imaginary part of r cis theta, or the imaginary part of r e to the I theta, however you prefer to write it. We know that that is r sine theta. So let's try and write these sinusoidal functions, f1 and f2, as the imaginary part of a complex number. So our first function, f1 of x, we said is, or we can see here, is sine of x. Great. Let's say that that's the imaginary part of some complex number. Now, looking up here, I can see that I'm going to rewrite that as, well, I'll keep it as r for now. We can see that the modulus is in fact 1, but let's write r just for completeness sake. E to the I, and it's this theta that I'm interested in. Well, I can see that that theta is this value here within the sine function, and for us that is just x. So I can say it's the imaginary part of I to the ix. Okay, we can see that there's effectively a 1 there. So I could just write that as the imaginary part of e to the ix. Great. I can do the same thing with my second function. So my second function is, let's do that in red actually. My second function is sine of x plus pi over 2. Well, again, let's write that as the imaginary part of modulus e to the I times, and in this case, my theta, now theta here is x plus pi over 2. Great. And again, I could write that without the r because in this case we know it's 1. So that means that my third function, where I'm just adding the two functions, well, we know that we can just add imaginary parts of complex numbers and they just become the imaginary part of the resulting complex number. So it will just be the imaginary part of re to the ix plus re to the ix plus pi over 2. And we don't really need those r's. We could write it without them, they're just 1. Okay, why is that manipulation useful? That manipulation is going to be what we use in lots of problems about combining or superposing two different sinusoidal functions and finding the amplitude and the phase shift. So we're going to use that technique in the following example. So we have an example. The voltages of two alternating current electrical sources can be modelled by the equations of the form V, the voltage, is equal to A sine Bt plus C. And we're told C is the phase shift. Great. The two sources have equal frequencies, so we don't know what the frequencies are, but we know that means B here is going to be constant. One has a maximum voltage of 60 volts and a phase shift of pi over 6. The other has a maximum voltage of 80 volts and a phase shift of 2 pi over 3. The sources are combined. Find the maximum voltage and phase difference of the combined source. Okay, so the first thing to do is to try and write out functions for both the first and second voltage source. So my first electrical source has voltage equal to something of the form A sine of Bt plus C, and we know that this A is my amplitude, and we know that because we've got no shifting of the principal axis, that's going to be my maximum voltage in this case. So in source 1, that's 60 sine of, and then I'll keep it as Bt because we don't know B, plus our phase shift of pi over 6. Okay, I can do exactly the same for the second voltage. This time it's 80 sine of, again, I don't know B, but I know it's the same for both of them because our frequencies are the same. Bt plus 2 pi over 3 this time for the phase shift. Okay, great. Now I want to add those two functions to get this resulting function of the combined source. So V3 is just V1 plus V2, and I could just write out 60 sine of Bt plus pi over 6 plus 80 sine Bt plus 2 pi over 3. And that's correct, that's not incorrect, but it's not helpful because I don't have it of the form that I want it. So I want it in the form f of x equals A sine Bx plus C plus D, so that I can immediately read off that amplitude and that phase shift. So I'm going to have to manipulate the functions in the way that we did previously, rewriting them as the imaginary parts of complex numbers. Okay, so this we said is not helpful. Let's rewrite these functions instead. So as a reminder to yourself, by all means, jot down that the imaginary part of a complex number z is just, okay, well that's the imaginary part of r cis theta, or if you want to write that as the imaginary part of r e to the I theta, both of those are fine. The crucial thing is that that is r sine theta. Okay, that is my imaginary part of the number. So let's take my first voltage again. So V1 is equal to 60 sine bt plus pi over 6. Now, I can see, looking at what's written here, I want to go from this form to this form. So looking at this particular voltage for voltage 1, 60 is my R sine, and this is my theta. So we have R sine theta as my function. Now I want to move from this form into the imaginary part of the complex number. So I'm going to rewrite that using my orange note up in the top right. Okay, that's the same as the imaginary part of R, so 60, e to the I and theta, which is bt plus pi over 6. Great, I've rewritten my first voltage as the imaginary part of a complex number. I'm going to do exactly the same for my second voltage. So my second voltage was 80 sine bt plus 2 pi over 3. And I know that this is R sine and this is theta, which means I can write that this is the same as the imaginary part of the complex number 80 e to the I, and theta is bt plus 2 pi over 3. Okay, that's all well and good. We've now written our two sinusoidal functions as imaginary parts of complex numbers, and we said we were doing this to make it easier to sum them. So the next thing I need to do is I need to sum them. So my third voltage, V3, now we said when we added the imaginary parts of complex numbers, we just add them together as normal numbers and they become the imaginary part of the resulting complex number. So it's going to be the imaginary part of, and 60 e to the I bt plus pi over 6 for that first voltage, plus 80 e to the I bt plus 2 pi over 3. Great. Then I'm going to do a little bit of manipulation just to try and factorize out anything involving this bt because it's unknown. So if you remember, as a little side note, if you have e to the I bt plus pi over 6, well, I can rewrite that as e to the I bt plus I pi over 6. And by our rules of exponents, we know that if we have two exponents added together, that's the same as multiplying two of the same bases raised to that power. So e to the I bt multiplied by e to the I pi over 6. So just a quick refresh to make sure you're comfortable with that algebra. You need to be incredibly comfortable doing that. So I'm going to rewrite 60 remains the same, and then e to the I bt plus pi over 6, I'm going to rewrite as e to the I bt, e to the I pi over 6. I'm going to do the same thing, e to the I bt times e to the I 2 pi over 3. Why have I done that? It means that I can now factorize out my e to the I bt, so the imaginary part of, take out my e to the I bt, that's then multiplying everything I've taken it out of, e to the I pi over 6, plus 80 e to the I 2 pi over 3. Okay. What was the point of doing this? Why do I care? Why is that something I want to do? Well, looking at this now, everything here is a known value. My unknown are b and t, and they're outside of this. So this is a known complex number. It's not written very nicely, but I can just use my calculator on my GDC, and I can say that this number, 60 e to the I pi over 6 plus 80 e to the I 2 pi over 3 is about, it's not perfect, but we can round 100 e to the 1.45i. Great. So once again, I can write this, and instead of this long 60e to the I pi over 6 plus 80e to the I 2 pi over 3, I can just write this as 100 e to the 1.45i. Great. Now, using my laws of logarithms, my laws of exponents again, I can combine and factorize those powers. So 100 e to the, and it's going to be ibt plus 1.45i. So let's take that factor of I out, bt plus 1.45. Okay. Why is this useful? Well, let's not forget, as we jotted down at the very beginning, the imaginary part of a complex number, r e to the I theta, is just r sine theta. So we used that all the way through this. We're going to do the same thing. We're just going to convert our current expression from this format, which we have it in, into this format. And we can see here that 100 is r, and bt plus 1.45 is theta. So my final statement to write out is that v3, this function, is just 100 sine bt plus 1.45. And that gives me my sine function for the third voltage in the format that I wanted. I can see straight away that my maximum voltage, in this case will just be the amplitude, that's going to be 100, and my phase shift is going to be 1.45, working in radians, of course. It seems like quite a complex process. The method, once you get used to it, you'll become comfortable with the decisions you need to make. You're converting into the imaginary form of a complex, the imaginary part of a complex number, and then rearranging and then back out so that you get a nice, neat sinusoidal function. There are a couple of formulae which summarize this, but I think it's much more useful if you are comfortable with the method, but they're in your notes if you wish to use them. Okay, and we can check. Let's check that what we got made sense. Now, deliberately, you can see up here, we have the function that we worked out, and b has not been given in that question, so we cannot just type it into our calculators. But let's assume that b is 1, and you can absolutely type those initial functions for the first volume, so for the first voltage, so f1, which you can see in blue, and the second voltage, f2, you can see in red, and that gives us our third voltage. So if in your calculator you can plot this function, and you can see and you can check, does it make sense based on what we've got? Do we have an amplitude in this combined function of about 100, or a maximum voltage? Yes, that looks about sensible. Do we have a phase shift, so to the left from 0, of about 1.45? Yes, there's 1. So that looks about reasonable as 1.45. So we can sense check the answers that we get. Okay, what I recommend is that you try a few of the questions below in the notes just to become comfortable with the method.